Hello everyone, my name is Osama. I am a PhD student in the OR Department of Columbia, and today I will be presenting some distributed algorithms for matching in hypergraphs. This is a joint work with my advisor, Professor Clifford Stein. I will start this presentation by motivating the problem of finding large matchings in hypergraphs. Then I will proceed to formally define the problem and discuss the choice of the MPC model as the parallel computation model that we use. Finally, I will present some of our results, namely two of the techniques that we use, the greedy approach and the HEDCS subgraphs. Let's look at combinatorial auctions and how to determine the winner to start. In a combinatorial auction, the auctioneer has multiple items he's willing to sell for a given price, and there's a set of bidders who are allowed to simultaneously bid on any number or any combination of items within their budget, but an item can be only ultimately assigned to at most one bidder. Therefore, to determine the outcome of such an auction, one needs a set of pairwise disjoint bids such that every item goes to at most one person. And to maximize the revenue of a combinatorial auction, one needs to solve the problem of finding the biggest or the maximum set of pairwise disjoint bids. Another problem in which we need to compute pairwise disjoint sets from some universe of elements is the airline crew scheduling problem. We have a set of airplanes, and each airplane needs to be assigned to a crew, that is, a pilot, a co-pilot, navigator, flight attendants, and so on. But there could be some constraints on the possible crews that can be formed. There could be constraints based on the training, which pilot can fly which airplane, which languages are spoken by the flight attendants. There could be some personal conflicts between the different possible crew members, and there also could be some availability constraints. Given all these possible crew and plane combination, any crew member can be only assigned to at most one plane. Therefore, a feasible schedule will be a set of pairwise disjoint combinations between airplanes and crew members. And to maximize the utilization of the resources, we need to compute the biggest cardinality or the biggest set of pairwise disjoint combinations of airplanes and crew members. The previous motivation problems can all be formulated in the language of hypergraphs. A hypergraph is given by two sets, a set of vertices V and a set of hyperedges E. A hyperedge is simply a subset of vertices and can contain any number of vertices. In the combinatorial auction example, vertices can be seen as items and hyperedges as bids. And the flight scheduling problem, vertices can be airplanes and crew members, and hyperedges can be possible combinations of airplanes and crews. A hypergraph generalizes a graph in the sense that in a graph, an edge links exactly two vertices. But in a hypergraph, a hyperedge can contain any number of vertices. If all the hyperedges in a hypergraph contain exactly d vertices, we will call this hypergraph d-uniform, and we will only consider d-uniform hypergraphs in this presentation. We will also use the term edges to refer to hyperedges when there is no confusion. A subset of hyperedges, or edges, M, will be called a matching if every pair of edges from this subset have an empty intersection. That is, M is formed by pairwise disjoint edges. The two pictures show two examples of matchings on the hypergraph of the previous slide. The first matching has only two edges, while the second matching has three edges. But we can see in both matchings that every pair of two different edges has an empty intersection. The d-uniform hypergraph matching problem is the problem of computing the maximum cardinality matching on a d-uniform hypergraph. That is, the matching with the biggest or the highest number of edges. In graphs, that is, when the value of d is equal to 2 and an edge can only contain two vertices, the problem is simply known as graph matching and is known to be solvable in polynomial time, and there are plenty of algorithms for that. What's interesting is that once the size of hyperedges d grows higher or equal than 3, the problem becomes NP-hard. Furthermore, it cannot be efficiently approximated within a factor that is better of d over log d unless p is equal to np. And the best known approximation ratio that we know is d plus 1 over 3, and coming from a local search approximation. In this work, we are interested in solving the d-uniform hypergraph matching problems for massive graphs in parallel. The reasons behind this choice are that graphs and hypergraphs can be very big nowadays and are of increasing size, and so they raise the challenge that the whole hypergraph cannot fit into the memory of one machine. Therefore, we would need to distribute the hypergraph over a number of machines, and we can only afford to look at a small fraction of that input once at a time. Another reason to motivate the study of hypergraph matching in parallel is that all the efficient algorithms and approximation that we know to these problems are based on local search heuristics, and therefore it is not clear that they are easily parallelizable. We therefore choose to study this problem under the massively parallel computation models, also referred to as MPC, which is a widely used model to solve different graph problems such as matching, vertex cover, independent set, etc. And I will lay out the dynamics of how this model works. We assume that we have an input of total size equal to big N that should be distributed on K machines. And we also assume that each one of these K machines have a memory per machine equal to S, such that S should be bigger or higher than N over K. This constraint simply ensures that the union of the machines are able to fit the whole input. The input of the hypergraph, that is, the vertices and edges, are initially distributed across all the machines. The computation in the MPC parallel model proceeds in synchronous rounds. That is, in each round, every machine would perform some local computations and then sends or receives messages to possibly any other machines. So to recap using pictures, we would have the hypergraph initially distributed across all the machines. And then in each round, each machine can perform a local computation without communicating with the other machines. At the end of the round, the machines can communicate with each other under their memory requirements with a possibly an all-to-all communication. And there are 3 criteria to make a good algorithm in the MPC parallel model. The first one is the memory per machine. We would like an algorithm that operates with a small memory per machine compared to the size of the input, ideally sublinear in the size of the input. The second criterion is the number of communication rounds. Ideally, we would like an algorithm that computes a solution within a constant number of rounds or a logarithmic or polylogarithmic number of rounds in the input. The third criterion is the quality of approximation. Knowing that the d-uniform hypergraph matching problem is NP-hard, we would like an algorithm that computes a good approximation, that is, a solution that does not deviate by much when compared to the optimal solution. The problem of finding maximum matchings in graphs when d is equal to 2 in the MPC model has been studied extensively. The table shows an example of some of the results on the problem. We can see that there's, for instance, a result by Asadi et al. That computes a 3/2 approximation to the maximum matching in 2 MPC rounds using a memory per machine of n square root of n, where n is the number of vertices. There are also some results that compute an almost optimal approximation to the problem with 1 plus epsilon being a small constant, but as a trade-off, they do require more rounds, usually sublogarithmic in n, and also require lower memory per machine. And the objective of this presentation is to present some parallel algorithms for the d-uniform hypergraph matching problem in the MPC model when the size of hyperedges d is bigger than 3. In this paper, we present 3 different algorithms that highlight the different trade-offs between what's possible in terms of approximation ratios as well as number of rounds and memory per machine. In this presentation, I will focus on the first and the second algorithms. They both have an approximation ratio of big O of d square and the number of rounds equal to 3, but they differ in the memory per machine requirements. The second algorithm that I will not cover in this presentation is a D approximation that necessitates a linear amount of memory per machine and operates within a number of rounds bounded by big O of log n. A very natural idea to solve graph problems in general in the parallel model is the following. Since we can only afford to look at a fraction of the input on each machine, simply solve the corresponding problem on each machine and then combine the different solutions to come up with a solution to the original problem. This is a formal description of the greedy approach that I talked about in the previous slide. So we can start first by assigning the hyperedges randomly to the machines 1 and k, and if g to the I is the resulting subgraph on the ith machine, then we will just compute a maximum hypergraph matching on this subgraph, and then we will go over all the machines from 1 to k, and we will take the union of the matchings without violating the matching property. That is, if there's a new edge that matches an already matched vertices, then we will just discard this new edge and keep the old one, thus giving us a set of disjoint hyperedges. One of the challenges that can arise with this greedy approach is that every machine will compute its own matching locally and without any coordination with the other machines. This can result in a set of hyperedges that have a non-empty intersection across the different machines, and that implies that when we will do the combination of the different matchings, we will be obliged to delete a big part of the edges because they will have a non-empty intersection in between them. Therefore, this will make the output of the algorithm a small matching. But we show that the greedy approach, even though it lacks coordination between the machines, still gives a big O of d square approximation. In fact, we show that even if we assume that the first I-1 machines have matchings that have high intersection between the hyperedges and therefore miss a big part of the optimal size matching, we show that even under this assumption, the following matching, the matching that is computed on the ith machine, will actually compensate for that by picking a big fraction of the optimal edges that will appear in its subgraph. By using this compensating property, we show that the greedy approach yields a big O of d square approximation to the D-uniform hypergraph matching problem with a high probability, whereas the probability corresponds to the randomness that occurs when we initially distribute the hyperedges across the machines. We also show that this greedy approach can be implemented in 3 MPC rounds, and that it necessitates only a memory per machine of big O of the square root of n times m, where n and m are the number of vertices and edges of the hypergraphs. The greedy approach is essentially optimal when it comes to the number of rounds. It only needs 3 rounds. Its big disadvantage, though, is that it requires exponential computations. In fact, every machine is required to solve the maximum hypergraph matching problem, which is NP-hard and in a worst case can take an exponential amount of computation. In practice, however, we will compute maximal matching instead of maximum because it is easier, and while it lowers the theoretical guarantee of the algorithm, it keeps it practical. This possibility of worst case exponential computation of the greedy approach makes us think about maybe another local computation that we can make in every machine that wouldn't require exponential time, but would still lead to a 3-round algorithm with a good approximation. So the question that we are asking is, can we compute the subgraphs on each machine such that when we take their union or their combination, if we name it H, then we would like ideally 3 properties. That H contains a large matching compared to the original hypergraph G, that H is much smaller than the original hypergraph and therefore we can fit it on one machine and output it. And third, that H is defined on each machine by a local constraint so that each machine can compute a part of H without having to coordinate with the other machines. And the answer to this question is more or less yes. In fact, we look at the graphs case with d equal to 2 and to the work of Bernstein and Stein in 2015, in which they defined an intermediate subgraph called the EDCS, or the edge degree constraint subgraph, and show that these EDCSs are a good candidate because they contain a large matching and can be computed in parallel. The formal definition of an EDCS is the following. For a given graph G, we need two parameters beta and beta minus that are both positive, and then we can define the corresponding EDCS as the subgraph H such that we have two properties. The first property is that for any edge u and v in H, the degrees of u plus the degree of v in H needs to be smaller than beta, and for any edge uv that is not in H, the sum of the degrees of u and v in H needs to be bigger in beta minus. The two properties of an EDCS aim to balance the different degrees between the edges that are taken into the EDCS and the edges that are not. The picture shows an example of a graph G and then an example of an EDCS of this graph with the parameters beta equal to 3 and beta minus equal to 2. We can see, for instance, in the red edge on the bottom right corner that the sum of the degrees of the two vertices that constitute this edge is equal to 2 and therefore smaller than beta, which is equal to 3. We can also see for any edge that does not belong to the EDCS that the sum of the degrees of the edges that of the vertices that constitute this edge is bigger than 2. In their work, Bernstein and Stein show that for any graph we can have an EDCS for any set of parameters such that beta is strictly bigger than beta minus. They also showed that it is possible to construct an EDCS with any set of parameters in parallel model in just 2 MPC rounds with a memory per machine that is only big O of the square root of n times m. Furthermore, they showed that for a set of specified parameters, an EDCS would contain a large matching, namely 3/2 approximation for the maximum matching problem in graphs. In our paper, we generalized the notion of EDCSs to hypergraphs, and we provide the definition of what we call an HEDCS, a hyper-edge degree constraint subgraph, which also takes two parameters, beta and beta minus, and is a subgraph of G defined by the two properties. For any hyperedge of this subgraph, the sum of the degrees of the vertices in this hyperedge are less in beta, or for any hyperedge that doesn't belong to this subgraph, the sum of the degrees of the vertices in H is bigger than beta minus. We also show that for any hypergraph G, an HEDCS exists for any set of parameters beta and beta minus under the condition that the difference between beta and beta minus is higher or equal than d minus 1. And the main result of our paper is to prove that this generalization, HEDCS, contain large fractional matchings even for hypergraphs when d is bigger than 3. And to briefly present a fractional matching, it is simply a mapping from the set of edges to the intervals 0 and 1 such that every edge E gets a value y E that is between 0 and 1, and that verifies also a constraint such that for every vertex the sum of the values that are assigned to the edges to which V belongs should be less than 1. If we have a fractional matching, then the value of this fractional matching would be simply equal to the sum of all the values of the edges. And in this paper, we are interested in a specific class of fractional matchings that we call the epsilon restricted fractional matchings, which verify an additional constraint, which is basically for every edge, the value assigned to this edge is either equal to 1 or in an interval between 0 and epsilon, where epsilon is a very small constant. These epsilon restricted fractional matchings are interesting because they either take the whole edge or they take a very small fraction of an edge. In this sense, they are very close to integer matchings that either take a whole edge or do not take it at all. We show that for any D-uniform hypergraph and small epsilon, there exists an HEDCS for specific range of parameter that contains a large epsilon restricted fractional matching, namely an epsilon restricted fractional matching that approximates the optimal matching with an approximation ratio equal to d over d squared minus d plus 1, which is slightly better than d, which is the approximation ratio that would be yielded by a maximal matching. We further show that the class of HEDCS subgraph is robust under edge sampling. That means if we take an original HEDCS and edge sample from it, then the outcome will be an HEDCS from the sampled subgraph. Another result that we are able to show is that if we compute an HEDCS of the subgraph on each one of the local machines and take the union of them, then the output will be an HEDCS of the original hypergraph. These two results can allow us to formulate the following lemma that shows that for any D-uniform hypergraph with D higher or equal than 3, an HEDCS can be computed in only 3 MPC rounds with a memory of big O of n square root of n times m memory per machine in general, and if the hypergraph is linear, which means if the edges of the hypergraph can have only one intersection at most, then we would need lower memory. We will only need big O of square root of n times m memory per machine to construct an HEDCS. We are now ready to combine all the previous results on the HEDCS class of subgraphs to formulate the following algorithm. We can start by randomly partitioning the hyperedges across all the different machines, and every machine we can compute an HEDCS to the subgraph presented on this machine, and we can take the union of these subgraphs and make them fit on one single machine. By the previous result, this union of HEDCSs will be an HEDCS for the original hypergraph, and therefore will contain a large epsilon restricted fractional matching. After that, we can simply compute a maximal matching on this union of HEDCSs to output a large matching when compared to the optimal matching of the hypergraph. So to summarize, in this paper, we present the first study of the D-uniform hypergraph matching problem in the MPC model, and we present 3 algorithms that highlight the different trade-off between the number of rounds, the memory per machine, and the quality of approximation. The other algorithm that I haven't presented here is a generalization of a maximal matching algorithms that computes a D approximation in big O of log n round. Furthermore, in the paper, we present an extensive comparison on real and random data between the 3 different algorithms. Thank you very much for listening, and I will be happy to take any questions.